Hello, I'm Doug. This is a talk on upgrading tensors to mathematical fields. I presented it at the April APS meeting in Denver, Colorado. What is featured is the covariant derivative of the standard model. There are three tensors there, B mu, W mu, and G mu, that are paired with three groups, y, tau, and lambda, and it is my hope that maybe we can find a mathematical field which can do both tasks, and we can make this a little bit kind of more dense, and that might even have implications to what it all means. Mass is broken at all scales that we look at it, and that's the sign of a math issue. At the atomic scale, we have the standard model, which works fine so long as none of the fundamental particles have any mass. That clearly is not the case. That's why our favorite hypothesis involves the Higgs mechanism, which uses a false vacuum, and when that false vacuum kind of symmetry breaks, then particles get a mass. Now, we haven't found that Higgs particle yet, but we've got an $8 billion bet going on at the LHC, Large Hadron Collider, out in Geneva. And it's very important that we find that, or maybe we'll have to find the math issue under a different math issue. For the galaxies, like a thin disk galaxy, if you were to nudge it on its center, then the whole thing would curl up into a ball. The solution is not mathematically stable. And yet we know that thin disk galaxies occasionally collide, and that is basically quite a little bump on the axis, and yet they don't curl up into a ball. If you look at the outer regions of such a galaxy, at the gases moving around, our current theory predicts that they should be slowing down, and instead they keep on going at the same velocity. Now, our hypothesis to deal with these problems is known as dark matter. Now, despite the fact that we know of so many particles, and we know in impressive detail how to do calculations with all the known particles, this stuff outnumbers the stuff we understand by a factor of, I think, about 5, and yet we have no concept of how it could fit in with the rest of known particles. We have problems at the universe scale, because relatively recent astronomical data indicates that stars are actually moving away from each other faster, which seems kind of, well, like it doesn't make any sense, because gravity should be, say, slowing them down. And the current hypothesis to deal with that, it goes under the name dark energy, and there are several studies out there for people trying to determine what it is made of, because it looks quite bizarre, and it doesn't fit in with any kind of known material that we've come across. And even the Big Bang, the origin of the universe, has two problems. One is it's mathematically unstable. To have a universe that's lasted as long as it has, you would need to fine-tune the parameters to like 100 significant digits, or it would like either blow up too fast or curl up and not escape. And another problem is that everything, according to the cosmic background radiation, is traveling at about the same speed, I mean to 5 significant digits, and yet they weren't close enough to each other to agree to what that speed was. So that miracle is solved by inflation, so long as there's some material that knows how to make the universe inflate. And we really don't know of any such material that would have that rather miraculous property. So I say let's go back and take a good close look at the standard model covariant derivative, which actually unites groups with potentials, and see if we can change the accounting that we use for it, and that may fundamentally change the math that we use from here on out. So there are these three group potential pairs, y with b, tau with w, and lambda with g. The four vectors are the b, w, and g, and they are formally groups under the addition operator. So their inverses would be minus b, minus w, and minus g, and 0 is the identity. Y, tau, and lambda are groups under multiplication, where you have 1 as the identity. And a mathematical field has both addition and multiplication. So the structure of this equation suggests that we should go and find a mathematical field that can accomplish these tasks. Particularly when you notice that there are these internal symmetries, that I and the A, that show that the group generator and the potential had to march together. I mean, that's a little suspicious. I'm going to create variations on the Maxwell action by upgrading from tensors. So let us start with the action for electromagnetism, because that's the basis of our most successful field theory of all. And I've written it so that it'll work fine in curved spacetime. And what we get out of here when we vary this action with respect to the potential is about the simplest darn wave equation you could form that had U1 symmetry. As you get skilled with action, you should be able to spot that this one conserves energy by saying, well, if I varied that action with respect to time, would I change the kind of integral that I got if I integrated over different periods of time? And the answer is no. Varying the time doesn't change that action, and therefore that's a symmetry. And because there's a symmetry, there must be a conserved quantity, and that conserved quantity is energy. You can also vary that action with respect to where it is in space, and that leads to conservation of momentum. You can also vary angles in here, and that won't change anything, and therefore angular momentum is conserved. And that subtraction step in there actually leads to a type of gauge symmetry that conserves electric charge. Now, one thing that doesn't come out of this equation is what the metric, how to constrain the metric. And so therefore you actually must supply the metric as part of the background mathematical structure. So we're going to try and do more with less. So all I've done is erased the Greek letters. I didn't like those Greek letters anyway. Of course, this looks like it equals 0, but hold on just a moment. Does this make any mathematical sense? Well, if those are still tensors, then no, because you needed the Greek letters in order to know how to combine them. However, this works in 4 dimensions, and 4 dimensions is kind of special in mathematics because they can be multiplied by one another. And so these are a group under addition, and they are, and modulo the 0 guy, it's also a group under multiplication. Now, to get to a correct action, we had to throw in a conjugate there and then change the order of this. And if you actually were to crank that out, it is a minus e plus b and a minus e minus b. And if you then take the quaternion product of those two, then you end up with exactly the same terms as show up for the Maxwell action when written with tensors. So because it's an exact match, there really is no new physics here. It's just a new nomenclature. But it's more than just a new nomenclature because, oh, actually, I should point out one other thing. This does have a 3 vector to it. And the 3 vector turns out to be the pointing vector, which is very important in EM, and we just get it for free. I don't think that's just a happy accident. I think that's a message to us. But if I want to do the action, then yes, I would isolate the scalar away from the pointing vector and proceed. But now that we have this new nomenclature, we actually have a new power. And the power is the power of substitution, because we can substitute things with different symmetries. And the group SU2 is actually known as the unit quaternions. And one way people write that is as the exponential of one quaternion minus its conjugate. So that will have 3 elements to its Lie algebra. And what we can do is wherever we see an A, we put in the exponential of A minus A star, and the resulting action will have the symmetry of SU2 in it, and therefore it will conserve 3 charges, which is good because that's what the weak force needs. To get to the electroweak symmetry, we take the exponential and we multiply it by a quaternion normalized to itself. Now, the group U1 is usually discussed as a complex number normalized to itself, a unit circle in a complex plane. Well, a quaternion is just 3 complex numbers that share the same real. And while quaternions don't in general form an abelian group, they do in the case of a quaternion multiplied by itself. So because it's A throughout that story, then that will have U1 cross SU2 symmetry. And then what about SU3? Well, that has 8 generators. And so if we just multiplied 2 quaternions together, it would actually have the same multiplication table as U1 cross SU2. So we totally need that conjugate in there to end up with a different multiplication and have a different group. And because, well, if those A and B are normalized, then we would have, 8 independent elements, and it has a norm of 1. And so I think that's a way to represent the group SU3. Now, I haven't mentioned gravity. Why is that? Because quaternions can't do the job. We have lots of data that says gravity can be characterized by a dynamic metric. A metric is a symmetric object, and as it changes depending on where you are in the gravity field, those changes too will be symmetric. So if we want to characterize this symmetric thing, then we need something that's every bit as symmetric. And so that's why I think we need hypercomplex numbers. Now, I'm not able to go into the details of that very specific proposal because this is only supposed to be 10 minutes, and no, it's when I record it ends up being twice or more than that. But I did not go into that hypothesis of mine for explaining a new road to gravity. But I think the kind of deep message is that we need to use the best possible mathematical field for 4D space-time physics. And currently we really rely only on the real and complex numbers. So let's at least take a good close look at them using graph theory. In graph theory, you have a vertex and an edge, and you label both of them, And the idea is that you take the vertex, multiply it by the edge, and it brings you to another vertex. So the real numbers have a vertex that's 1. Multiply by 1, it brings you back to home. And I actually think that has enormous, deep philosophical implications that I won't go into right now, unless we go out to a bar or something. But I think I think that loop is very important, because when we compare it to the complex numbers, that imaginary factor doesn't have a loop. You can't take I, multiply by I, and get back to I. It doesn't work that way. Instead, you have directional derivatives. Sorry, I keep on doing that. You have directional edges. Okay, so 1 times I brings you out to I. To get back, you can't go that way. You go I times minus I. That'll bring you back to 1. So the quaternions now have, instead of 1 imaginary factor, I, they have 3, I, j, and k. So they have this directional edges kind of thing going on there between 1 and I, 1 and j, and 1 and k. And if you say, well, how do you move about from I to k and whatnot? Well, then there's one way that will be a j, and the other way, the way back, is a minus j. And so this, we started with the reals, which had, only undirectional edges. The complex numbers, where it was 50-50, and then the quaternions, where directional edges really just dominate. Well, if you've ever built graph theory using clay and pipe cleaners like I have, then it's really a pain in the arse to have all these two pipe cleaners that have to go to the same darn vertex. So you just say, I hope somewhere some mathematician has come up with a type of number where I only have to use 1 pipe cleaner. And it's officially called a hypercomplex number. And so 1 times I brings you out to I, and I times I brings you back to 1. It's great. Very simple. And it is my belief at this point that I can actually back up with a scary amount of math that might be the road to a new approach to gravity. And I just want to end with a plug for my website, visualphysics.org, because it's really kind of a Don Quixote mission to try and change accounting for physicists. I mean, those guys are so good with numbers, and they are confident that, the underlying accounting is just fabulous and is just amazing, and it is just super powerful. I mean, tensors are how you write the standard model. It's how you write general relativity. It's how you do string theory. And I just want to say, well, that's true, but they could be better. I mean, if you could also multiply them. Now, the cost is that you can't do this in arbitrary dimensions. In other words, string theory is dead by accounting rules, not by you're not smart enough, or this isn't really fascinating or amazing, but the accountants say, no, we live in 3 dimensions of space with a clock on the wall ticking as a scalar, and you had to work with those constraints. Too bad. I don't know how I'm going to sell that, like, ever. So I've set up this website. We've got forums where a few folks are chatting away. It's kind of fun. Quite a number of tutorials, because this stuff really is hard to understand. These animations are, because we really are doing math with time, and we kind of only have a couple of ways we think about time. Like, we get older and we have a couple of cycles going on, but to just really start doing all kinds of crazy math with space-time, things get insane like almost immediately. So there's also downloads there, and our finances, and yes, we do have a slam. So we're trying to be playful in our critiques of other people who are studying these fundamental things in nature. So I hope you enjoyed this talk. I certainly have enjoyed studying all this stuff and sharing it with you. Thank you very much.